This is, as Simon has already alluded in that great little intro. Actually, I haven't seen that. I'm an airline pilot, as it said, for British Airways. So I fly the 787s around the world. And when I'm not doing that, I work as a freelance .NET Xamarin IoT developer. If you want to reach out to me, you can see my Twitter handle and email address on the slide, and it'll be on every slide from now on. But I'm not here to talk about that. I'm here to talk about how I helped a young lad with a 3D printed bionic hand, a little bit of IoT, and a Xamarin mobile app. So there we go. So as I say, my job is flying an aircraft around the world, and that's the flight deck of a Boeing 787. Now, I'm not mentioning the fact that I'm an airline pilot just because on the show off. Look at me, I'm an airline pilot as well as a coder. You know, I can do what you do and more. It's not about that. I'm sort of barely dangerous as a developer. I'll come back to why I mentioned as being an airline pilot later on in my talk, but it is quite important to this project and where we see it going forward. My passion's coding, developing things, playing with electronics, IoT. I love learning new things. I'm all about learning, on the Learn platform of docs.microsoft.learn, and supporting others to learn as well. So I'm more than happy to come along to anyone's meetup group and talk about either IoT, Xamarin, or even how to do team building and teamwork that I bring from the aviation sector. But that's enough about me. As I say, let's move on. Let's talk about Caden. Young lads, he's 16 now. He was a little bit younger when we started this project, but as you can see there, in image, Caden was born with a limb deficiency. He was missing his left forearm, and you'll notice in the lower of the picture in the centre there, on his right hand, the hand it does have, is missing his middle finger. So his pinky, his little finger, and his thumb. So he calls it his claw hand because he kind of grips like crab hand because he grips like a crab. And then he also has a prosthetic arm provided to him by National Health Service, the NHS here in the UK, which is a wonderful, awesome part of the government system, helping us get through this pandemic, which is amazing. But let's move on and talk about what the NHS, the National Health Service, do provide for Caden. You can see there he's off to London 2012 Olympics. He's on the London Underground going along to the site. You can see his prosthetic arm there. So he would have been 8 or 9 there. Going off to London 2012, and that was his party trick, was to click his arm on something and step away from it, and everyone looks, that boy's arm's just fallen off. You can see there in detail the fact that it's just a claw with a formed, in that case, fiberglass and sort of coloured to look like a human arm, which Caden hated. And we'll come on to that in a little while. And then there's a bit of fishing line that goes across the back of his shoulders to strap on his other shoulder. And as he moves that shoulder in and out, it opens and closes the claw. So very, very basic. You can see there in the lower picture, you can see that every year he goes along to the hospital, sees his prosthetic surgeon, and they take a cast of his arm, of the part that he has, and they make him a new arm. But he keeps the claw. So every year he gets a new one. I've got the red one, the photo. The family have happily loaned to me for my talks, which is amazing. Every year since Caden's been born, unusual for him because when he was born, he went into a group that were looking into how to give prosthetics to children. So he was quite lucky to get into this group. So every year he gets a new arm from there downwards, and the wrist part unclips, and he keeps that until he breaks it, and then he gets a new one. Now, this arm costs the NHS, for them to produce it, costs anywhere between £4,500 and £6,500. So they're not cheap to make. It also takes Caden out of school for 2 days because he has to go along to be fitted and then go back to be checked to make sure it works. You've got all the technicians and the time and money that goes into their time behind. The hook that goes on the end costs anywhere between £2,500 and £3,500, and then it just has elastic bands here that pull it back together, and you can see the fishing line, £100 fishing line, which the family use and replace quite often when Caden breaks it. But it's quite a dumb instrument. So we go back to my slides. Thank you, Simon. We looked through it. Back in 2016, Christmas time in 2016, there was a news article on the BBC News and Sky News here in the UK about a dad that printed a 3D printed prosthetic hand. And, you know, back after the school holidays, because my kids go to school with Caden, or did, his mum come up to me in the playground and said, Cliffy, you've seen the news about this dad's 3D printing hands. Like, oh, yeah, I have. And she went, you got 3D prints, haven't you? And it's like, yes, I have. And I realised instantly what I'd fallen into, that trap where you kind of offer yourself up to help. But I was more than happy to help. So I went home and fired up the browser and started looking around. But before we look at what we found, let's see what Caden can do with his current arm, or what he had before. So if we just watch this, hopefully you can hear the audio as well. Not that you need the audio, it's just cups clean together. But Caden's quite adept at using his arm that he has in his hook. So, he can make me a cup of tea when I go visit. He can even pick out a tea bag and make me a cup of tea. And that's because Caden's used one since birth. And that's the reason. I'll just move on from that. So Caden's used one since birth. She's had many years, and human body is amazing. We can adapt to anything. So because of that, he's adapted and he's used an arm. But a lot of children that need a prosthetic limb is because they've had either a life-changing injury, or they've had an illness like, say, meningitis or diabetes, where they've had to have a limb amputated for various different reasons. So they've then suddenly got to try and learn to use a hook, which they're not used to. The hooks are quite expensive for the NHS, as I said earlier, and every year that's an ongoing cost for the National Health Service. But what if you're in a third world country? What if you're in a part of the world where there isn't a National Health Service? What if you're, in a part of the world where you have to pay for your own insurance, and they don't want to cover that cost, that ongoing bill for the child to have a limb? So what do you do then? So I thought to myself, well, let's see if we can make Caden an arm. So we then looked at where's my mouse gone? There it is. We then looked at hold on, there it is. We then looked at the internet, and the first thing we come across was the Limbless Association. Now, in my talk, anyone that's seen this talk before would know that I show a page where I show the links, and it says still under development. That disappeared about 2 weeks ago. So clearly, the Limbless Association has now had their developer. They give them a kick up the backside, because the last 3 years it said under development, and now this new fancy site has started to come together, which looks amazing. And maybe they've seen my talk and realised that they need to kick the developer. If that was you, I'm sorry for highlighting the fact you've been lazy for 3 years. But you can see here the Limbless Association. But you go in there, and it's they're a fantastic association linked to the National Health Service here in the UK, and they'll help you come through to find a prosthetic limb. But it wasn't what I was looking for. I then stumbled across a news article and dug a bit deep and found Team Unlimited. Where they are 3D printing, as you can see here, the Isabella edition arm. It's moved on since I was looking at this project 3 years ago, and you can see there it's hands, but you can see the section of in the 3D print here where the fishing line comes up and hooks to a hub, and then again it works in the same principle where you move your shoulder and it opens and closes the hand. In fact, we even made one of these for Caden. And he hated it because the fishing line came out the bottom, and as you moved his arm backwards and forwards, and the reason he hated it is because if I put it in front of the camera, it doesn't quite make a grip. So Caden was unhappy because he couldn't pick things up like he could with his hook. So it lasted all of about 2 minutes before he decided he didn't want it. So we went back to the drawing board. We then stumbled across the Open Hand project, which is 3D printed project, but it's got some motors inside. So now we're starting to talk. We're talking about robotics now. And as a person that worked in the car industry for 11 years as a robot programmer and software engineer, that's more my world. That's more IoT rather than just 3D printing something. You can see here that Joel Gibbard, the guy that invented this, picks out the fact that a prosthetic limb costs upwards of £100,000, $100,000, sorry, for full biomechanical with motors, etc. Prosthetic limb. So that's way out of the reach of even the NHS, National Health Service, unless there's a compelling reason, like you're a sports star or you need it because it's the only way you can live and carry out your job functions, etc. So again, this was a great project, and it was the start of looking into this. And then we stumbled across lost my mouse again. We then stumbled across Open Barnix. Now, Open Barnix is what Joel Gibbard went on to create as a company. And it's called Open Barnix because at the time, everything was open and on GitHub. You can see here, this is their Brunel hands that they produce now. And so you can go along to Open Barnix and buy one of their hands or arms, and they'll make it bespoke for you or your child. And they're trying to get it into the National Health Service, and I know it's available in the US and France and Germany at the moment, and they're trying to roll it out as a business. And good luck to them. It's amazing. The lives they're changing is fantastic. But we look at their GitHub, and so mine's in dark mode. I forgot to change it before the talk. We look at GitHub. You can see here the last commits were 3, 4, 5 years ago to the STL files. And the STL file is what you take and then you send to your 3D printer to print out. The electronics and software is even longer. So you can see the fact that they've not iterated on the design for quite a while. Even though us as the community we're putting in PRs, they're just not taking them in and accepting them. So we go back to if we minimize this, we should go back to my slides. So we've looked at Google and Bing, and I fired up the 3D printer and started printing. Now my RepRap Mendel printer that I had at the time was good at printing boxes for my IoT projects, but didn't really have the dexterity to print the small parts for hands. This is the index finger. It wasn't brilliant at printing that. So what do? Obviously, you upgrade. So this is the Prusa Mark III i3 printer. I've got 2 of them here off to my sides. I've got one which is the one that's built there, another one which my 11-year-old son built and put together with no help from me, other than me peering over his shoulder every now and again just to make sure the important parts were correct. And I'll come back to why that is later. The reason there's a blue part that's circled in the image there, it's a little bit dark actually, I should change the contrast on that image, is because when I was building the printer, I broke that part. I snapped it. So I fired up the old RepRap Mendel printer, and all I had was blue filament at the time. So I printed the replacement part, and all the black elements of that printer, except the main square frame in the center, all 3D printed by Prusa in a factory in the Czech Republic. So you could buy one of these printers. When I bought it, it was best part of £1,000, and now around 600. So what, $1,000 if you're in the US. And they ship all over the world. They're amazing printers. They are, top of line, far better than you'll get anywhere else for a home built 3D printer. I highly recommend them. I've got another one which has got a 5 filament spool on it, so I can take in 5 different colors as well. So we built that. We printed out all the parts. You can see there's all the white plastic parts. The red plastic parts are flexible filament, so they're like the tendons, so they hold it all together and keep it in place. In the top corner there, top left corner, we've got the 4 motors. They're linear actuators. You apply voltage to go in and out by 20 millimeters. There's a load of springs and dowels and parts and some little brass inserts. If you need a thread in a 3D printed part, these inserts you put in with soldering iron, so they heat up. You push them into plastic melts. You pop the soldering iron out, and it solidifies around it, such that you can then got a machine thread screw into rather than screwing in out of plastic. So we had all the parts, and then we need to connect it to Caden. So this is my 3D printer printed out a socket. So remember I talked about Caden's arm and how it connects to him. He has it remolded every year. We took one of the molds that the hospital provided. Their prosthetic surgeon was very helpful in providing that. And this is the plastic mold here. So we took this, and my oldest son, Macaulay, is a dab hand at 3D design. So he was going to the games development world, and he free drew that in Blender. And we printed it, as you can see there in the video. You can see there's 5 hours and 45 minutes for remaining. So I went off to bed, tend to leave the printer running overnight because it's normally pretty good at coping. Come back in the morning to 3D printer's worst nightmare. The print failed. You can see it popped off the bed, and it's just off the back here. It popped onto the windowsill, thankfully, and the printer just carried on printing in free air, which is why you got the spaghetti monster mess in the middle. But thankfully, it printed just enough that we could try it out on Caden. So we did that, and it didn't fit; it's too small. So we increased the size. We printed a second one, and that was too big. And in true Once Upon a Time Storyland, Red Riding Hood, we printed a third one, and it fitted just right. And there's version 3, as you can see there, Caden trying out to the point where he said it actually fitted better and it's more comfortable than the NHS one, just because we could blend off some of the corners inside a little bit easier for him. And that is the design we have now. And every few months, his parents or he texts me and says, it's getting a bit tight, can we make a new one? I print a new one. It's 6 hours on the printer to print off at least 80 pence, so less than $1 in plastic to print a new one. I drop it on his doorstep and him or his dad fits it to his arm and he carries on with his day. So, you know, it's awesome stuff and super cheap. No more of this thousands of pounds in NHS and weeks of waiting. So we see here, this is a spreadsheet I put together, all the 3D printed parts. Now, the molds at the top, these molds here in the hand, you can see it better on this hand here. These black elements, you don't want those because this is similar plastic to Lego plastic. So you don't want those because it's hard. You can't really grip things. So this is molded on, and it's a neoprene rubber. So it goes into a mold which looks like this. And we fill the reservoir with neoprene. We put the palm of the hand inside there, so there's a few different molds, and then we squash this down, and it squashes the resin in and molds. Leave it on the side for 24 hours, and then you take the screws out, pop it out, clean it up a little bit with a Dremel, and job done. It's literally, you know, about an hour's work to mold all the parts in total, and then you have all the parts molded on like this. Go back to my slide again, please, Simon. And you can see there, so the cost of the mold is total cost of £10, so what, $15, give or take a bit. And I've still got the same set of molds I made at the very beginning of this project, and I've probably made about 16, 17 hands now. I'm still using the same set of molds. So that's a one-off cost for a hospital or a unit somewhere in the world. To print the hand, though, we're talking £5, $6 or $7 for all that plastic, all these parts of the hand that you can see. That is it. And the only other part you need is the flexible parts. These are the red parts that you see that hold the fingers together up the sides and also the thumb as well. And you see in the earlier picture, that's 20 pence worth of plastic. But you need to buy a spool, which costs £30 per kilo. But I'm still on the same spool. And as I say, I'm using 20 pence worth of plastic each time. So the whole thing, if you take the molds away, comes to just over £5, so $6 or $7. So super, super cheap. Not the 6.5. To best part of 8,000 or 9,000 NHS to produce one of these, and then every year they have to change it. This is make it once, and then every year all I have to do is change the socket part, and then Caden goes off and uses it. So how do we control this? Well, OpenBionics had a board called Chestnut board, which was based on an Arduino chipset, the SAM DM0 chip. Was in there, and it was a homegrown, home designed chip which fitted in the back of the hand perfectly, and they had these built for themselves for their arms that they sold. But the problem they had was the fact that the boards were they made them in batches, and the problem was that they only sold on their store that I had at the time those that had left over, which was rare to find one. You could get one made, but they were very expensive to have one made, and obviously you wasn't 100% certain it's going to work when you made it. So I wasn't overly happy with the cost of the board, because if Caden then broke his board, he's a child, he dips it in water, that sort of thing, and it gets damaged, he's got to wait weeks if not months for a new one. It's going to cost hundreds of pounds. Wasn't working for me, wasn't happy with that. How do OpenBionics, and they've moved on from this design now, but how did they control this? Well, they use one of these, which is a MyAware muscle sensor. So these little muscle sensors, I've got one here, as you can see in the image, these here stick on your arm, and you stick the little the fly lead goes onto a junction, which is where there's no muscle, and it will sense the signal. So we can go back to slides again. And I'll talk through how it works. So what it does, you stick it on the center of the muscle mass, and that's the correct place, which you can see there in green, to get the most signal differential. If you stick it along the muscle center line, but near the ends, you'll get the intervention zone where you don't get enough signal. Even off to slightly to the side, you'll get the midline offset, which means you'll get no signal at all. And the junction is where the little fly lead goes, where you want to. So what you want is the biggest signal against the junction where there's no signal, which is the noise, effectively, the system. And it will give you a signal as to whether the muscle's being tensed or not. What do we do with that then? Obviously, you stick it on the muscle. That's not the scale. My muscles are nowhere near as big as that one, but you can see kind of the idea. Now, Caden had enough muscle mass in what was left of his arm from his elbow for us to stick the sensors on. He's weirdly are 90 degrees out to where you and I would have ours. So you stick the sensor on the inside forearm and outside forearm. And the reason you do that is you need a sensor for open and for close. So you need two sensors. These cost £35 each. So you need two sensors. The sticky pads, a pack of 50, cost £5. I know I'm doing this in sterling. I'm pretty certain you can work out the exchange rates to wherever you are in the world watching this. So these sticky pads need to be changed. You need 6 per day. So a pack of 50, which is going to last you just over a week. So that's an ongoing cost. The boards, this one's broke. It's been snapped already. Didn't last very long for Caden. So he's a child. He's going to break it. It's stuck to his skin. It's not going to last very long. It's not going to work. And they're expensive boards. So I didn't want to, didn't like that idea either. How does it work though? Well, we want to do open is, as you can see in the image there, and close. This is audience participation time. So if we can put your arms straight up like this, if we can go to a bigger picture of me, it's nicer to see. If we get our claw fingers, put them just either side of the muscles here. And then if you open your arm and put your palm out as in a picture, you'll feel the muscle at the back there goes tense. If we close our arm, so it's pointing towards us, the muscle at the front, the forearm muscle goes tense. If we hold a hand straight up and create a fist, both muscles go tense. So now we've got open signal, closed signal, and change grip signal. So now we've got a way of controlling our board. So Open Bionics come up with these 5 grips that they believe were the 5 most commonly used grips. And these are the ones they load in their things. But when we first tried this with Caden, he went, well, I want to play my Xbox with my friends. Can I have a special grip just for me? Well, okay, right, we'll put that on the to-do list. It went into GitHub issues, and we thought about it for a while, how we're going to sort this out for him. But let's look at how we control these grips at the moment. Now, this is all written in Arduino C. If anyone's played with Arduino C, it's a subset of C, C++ adapted for microcontrollers and given a bit of an Arduino flair. It's awesome. It's a great way to learn as well. But what they have is a 3D array. Now, if I zoom in on this to make it a little bit easier to see. So if we look at the point gesture, which is this one here, there's an animation array that runs and it counts from 0 to 100 over a period of time. And that is set in the settings. In Caden's arm at the moment, it's 1.8 seconds. So over 1.8 seconds, it counts from 0 to 100. And when it gets to 0, it sets the fingers positions to fully closed, fully open, fully closed, fully closed, fully closed. And then over the period of time, it animates. If it's blank, it looks at the previous one. So you can see there. And when it gets to 100, it fully closes, fully closes, fully closes, fully closes, fully closes. So you can see what it's doing there is it's closing all the fingers up. Now, the finger is... so the thumb is closed all the time, and you see the open, close, close, close. So it's creating the point gesture for making the point gesture of it's over there, and you're pointing to your best friend of where to go to get to the bathroom, for example. So you can see there. That's I've explained it. We're software developers. If I said to you go and make an Xbox script, you'd probably go away and spend an hour or so and be able to come up with an array that fitted in there that counted up. Similar to the pinch grip, which counts up 0, 10, 40, and 100. So it's got some steps in the middle. You could create one that gripped the Xbox controller, and every time you tense his muscle, it twitched the trigger finger. You could create one of those, but then you'd need the Arduino IDE loaded. You'd need all the SDKs and all the other things. You need the cable to plug in. You need to take the hand apart to plug the cable into the board. You'd need your laptop set up and plug it in to load the thing. Then you need to make sure it works and debug it. It's a lot of work. And we're software engineers. We'd know how to do it, but would a parent, would a doctor, would a technician in a prosthetic unit know how to do that? Possibly not. So again, that's something else that I wanted to fix. The drawbacks, I'm going to cover this quickly because I know I haven't got a lot of time here. But the processor boards is one-off supply. I want to fix that. The MyoWare sensors, they were expensive, and you need to play with them to tweak the muscle gain levels. And then the grips and seats if you want to get around. So I use Adafruit featherboards a lot in my IoT projects because they're awesome. You can get them anywhere, even from Amazon, and they're awesome. The feather unit here, the red section at the bottom there, that area there is the kind of area where they put the different sensors. You can get one with Wi-Fi, Bluetooth, LoRaWAN, etc., etc. So this one's got Bluetooth and a little antenna on the end there. It's got the same processor that was in the Open Bionics one. It's got a JST plug, which means you can charge a battery. Awesome. and it had everything I needed, all the analog inputs and outputs I needed. So there's some specs. I'm going to skip past that. You can look those up if you wish. So this is the circuit I built. And the other board that you can see here, so this is the Adafruit board here. The other board you can see there is the Merck controller board, also an Adafruit board as well. And that means I can just use I2C, which is a serial protocol, to talk to that board and say, move motor 1 to this position, and it sorts it out for me. I don't need to worry about it. And then the main processor can go back to doing other things, like listening to the analog input of the potentiometer that's built into the motors. The circuit there is, you can see, fully built a little bit closer. You can see there's also a Pololu voltage regulator in there, which is to take the voltage from the battery and step it to the voltage needed for the boards. And the reason they did that was because in the Open Bionics system, they have a big battery on the upper arm here, which is 14.4 volts. The motors draw 12 volts. And they draw quite a big current when they initially move, but then it's milliamps afterwards. You're only really moving a small amount, but they have a big battery, 14.4 volts, and that is from an RC car. So you use the same cells from that, which means you then need a specialist charger. I didn't like that. I wanted a charger that anyone's got, a USB charger. So I use these Anker power bricks. We've all got them. We all know them. We get them from conferences, hopefully. But this one is £20 from Amazon. It's a 10,000 milliamp hour battery. It will run the arm for at least a day, if not more, except Caden unplugs it to charge his mobile phone or his friend's mobile phone from time to time. So the Pololu unit there steps this voltage, which is 5 volts down to 3.3, which is required by the boards. And there's another Pololu unit. It steps up from 5 volts up to 12 volts, which is to power the motors, which works really, really well. Yet to burn any of the boards out, and Caden's been using it for quite a while now. The flat ribbon cable there, I need to wire on, so I need a bit of soldering there to get it to work, to wire on, to plug in the bits of the motors. If I go back, you can see there, I'm holding it in the right-hand image. I'm holding the flat ribbon cable come from the motors, so I needed to put some connectors on there. Bit of soldering, but other than that, it's a fairly simple circuit to build. So I've crossed off the processor. MyOS sensor then, how do we do this? I was flying to Japan. I remember the flight vividly. So somewhere over the middle of Russia, no one to talk to on air traffic control. And, you know, when there's not much to do, we'll read a magazine or flick through, you know, do a crossword or something in between running the aircraft. And I know you're probably thinking, my God, the pilots are watching, reading a magazine and not flying the plane. The all pilots flying the plane. And you become very adept to be able to read a sentence or two and then scanning up the instruments, having a look around, and then reading a sentence or two and looking around again. And it's otherwise you will get, sort of watching all the instruments all the time intently. Certainly in the middle of the night, you'll just become sleepy and drowsy. Imagine staring at your speedometer when you're driving and just staring at that, or even the lights on the night drive of the cat's eyes that fly past you on the motorway. It becomes a bit, so you have the radio on and you listen to music. We can't do that because we have to listen to air traffic control. So we'll read a magazine or something simple. So I was reading this magazine, Hackspaker magazine. You've not heard it, go to their website and sign up and get it. It's awesome if you love IoT. And this article is about Arduino debugging. You notice there that they're talking about Graham's Morrison is talking about Arduino debugging, and the sensor he's using there that is plugged into the board is a piezoelectric sensor, much like your piezoelectric sounder that's in your laptop or your PC, which makes a sound when you turn it on. It goes beep, beep, beep if you've got a memory problem, for example. That is where you apply electric voltage to the piezo crystal and then make a sound, so it vibrates. This one, if you knock it or bash it, it vibrates and creates a micro voltage output, which you can then measure. So that's what he was using this here. And there's a little resistor in the middle there, as a resistor bridge, just to make it work. So I landed in Japan. I ordered a pack of 10 of these, cost £1 delivered from Amazon. And how they can be made wherever they're made in the world and shipped to my door for less than £1, I do not know. But Jeff Bezos is a multi-billionaire, so he obviously knows how it works. So I got that. We tried it. It didn't quite work. Caden hated it because we could only sense the trigger of open and close. Couldn't control the middle. So SparkFun, another site I use for buying electronics, they have these force sensitive resistors, and you can see in the GIF there or GIF, depending what side of the fence you sit on. As you apply pressure, it changes the resistance of that resistor that it's built into. You put a resistor bridge across it as well. You can control how much it ramps up and down. And we fitted those, and I've got one. I did have one. It's around somewhere, and it's just fitted inside the socket. So you can see the pad there. On the back of it, it's got some 3M glue. So you peel off sticky things, stick it inside the socket, and there's no electronics then for Caden to damage as a child. There's nothing for him to break. So we've got rid of the MOS sensor. You can see there a pack of 2 for £6. So I've now gone on slightly bigger square ones, which are £5 each, purely because we needed the muscle sensor to a bigger area for the muscle to squish it. And because the plastic is hard, it's squashing it against a hard surface. So as you tense your muscle kind of grows in size, and it squashes this sensor against the hard plastic, and gives that a reading we can use and measure, which means now Caden can stop the hand mid-grip if he wants to do something different, or change to a different grip, or open again, etc. He can do all that because he's now got infinite control using that muscle sensor. So this is just a friction drawing of the circuit. It's put together. It looks complicated, but we just got the battery, the 2 poly units, one stepping up, one stepping down, 2 controller boards, 2 sensors in the corner, and the 4 motors. And I can build this. I've done lots of them now, but I can solder this together all in under an hour. I could probably teach you how to solder and put one together in 2 hours. Even if you've never soldered it before, it would take that long. So to teach someone, a technician in a hospital unit somewhere around the world, that's completely doable. Now we cross off the MyWare sensors. Now we come to the last bit, which is the other grips. Now, as I said, the sensor board has a Bluetooth transmitter on the end, and I write Xamarin projects, so we wanted to work on building something for that. If you work with Bluetooth, it's complicated, as in it's got so many different names, because so many different companies all vying for calling it and their name being the right thing. We went with Bluetooth Low Energy because we only need to send a packet of data, and then the device will turn off and reconnect later and send a packet of data. So the way Bluetooth works, I'm sure you know, is a central device, your tablet, your phone, your computer, which talks to peripheral devices, be that handy in the hand, your watch, your Fitbit, your Garmin, be that, I don't know, your car. When you jump in your car, you chuck your phone down and it talks to your car, etc. They're the peripheral devices. Central processor does the main thinking. That's it's still called master, even though really we should be calling it main now, but it's still called master. So we look at this. You see the master and the slave. The master and slave talk when they do the initial connection, and then agree a connection interval, which means then the master will at that agreed time will turn on and send a packet of data, and the slave will reply with its data or reply to the message that's sent. Then they'll both turn off until the next connection interval elapses. And you can set that connection time as wide or as short as you need it to be, and that's the way Bluetooth Low Energy works. How does that packet of data look? It's just much like a class that you have inside your .NET program, your C#. You have your class, then your service is going to be your model within that. Your characteristic is going to be each of the different properties within there. So your service could be heart rate for a watch, and then another one could be the steps. And then within that characteristic, how many steps a day and how many steps in the last hour, and the heart rate could be what is the instant heart rate, what is the heart rate over the last hour. So you can see how it builds up. So now if we go across to Visual Studio, and I need to get the right one. There we go, and that should resize. You can see here that we've got we just pull in the Adafruit parts for the Bluetooth and the libraries. It's all in C, as I said, and then we give it a name here, which is handy, and we set some factory settings, and then all we're doing is sending serial data backwards and forwards. So that serial data is just sent as a serial protocol using UART, which is the serial protocol using IoT, and it just sends commands backwards and forwards. So super simple. Just been told I've got a 5-minute warning, so I'm going to not labour this too much. And come back to my slides. I talked about the fact that I do Xamarin development as well. I'm going to blame Alan for this because he stole some of my time earlier, running 10 minutes long. So in Xamarin, you have traditional and Xamarin forms. Traditional is where it's all C# backend, but you write each of the different UI layers in iOS, Android, or UWP for Windows. Or you have Xamarin Forms, which is where even the UI layer is written in XAML or in C#, and it's shared across the 3 different platforms. With now .NET MAUI coming in .NET 6 in November, adding into iOS, Android, UWP. You've got Mac OS as well. And Community have also brought in TISM, which is the Samsung used for fridges and their stuff. So, it's growing as well. So look at the Xamarin Forms shell. And in fact, I'm not going to do that because I haven't got time to whiz into that. But in Xamarin Forms shell, you can create the app that you want. I want to get on to actually showing you this working. So what I do is I create the projects, and if I bring on Visor, which is here, and I just need to quickly close this and reopen it again and connect the hands. You can see here, this is my mobile phone that is in front of me. It's all written in Xamarin, and you can see it's not connected. Connect first, and I've tried to make this simple. So I'm going to connect the battery because it only does it on power on, and connect this, and we'll start scanning. The Bluetooth, you can see it's got Bluetooth there, and if we scan again, we've got Handy because it's been renamed now because the board's booted up, and it comes into the app. My son's, oh God. Get rid of that. Don't know why it's picked up calendar things. I thought I'd muted that. We go into the UART connection. I think let me do that again because that's interrupted what I was doing. So connect, do this. There, we'll start scanning, and we got Handy. So go into that. It's now connected. Stop scanning, and then we go into the UART. And we'll see the fact that it should, there you go, start talking. So now they're talking between the two. This is got, this UART connection at the moment is set up for me as the developer. So it's sending stuff that would stream out to my laptop that I can see. So you can see the commands there for setting it up, and it's got some settings in there already. But if I go back to the grip selection, you can see here is all the grips. And this is a carousel view, and you've got some there that are grayed out because they're disabled. You can see there that I'm controlling by just tapping the screen. So I've got the fist grip there, and you can control this. So there you go, even better. So you can see this is the hand moving. You can see Caden's got control of the fist grip, and we've got a point gesture. So it's over there, mate. You can go that way. And you can see also in the top, we've got the heart, so you can make it a favourite and the likes. If we go across the grip order, Caden may not want fist grip, hook grip, point grip. Maybe he wants to point first because he's kind of telling people where to go. So you can put that at the top of the list, save that back to the hand, and now that's the order. You remember I said earlier, you can open, close, and your fist control the grip. When you close your fist, it will go to the next grip in the grip sequence. So he has 3 grips in his grip sequence there because if you go back to the grip selection, they're the 3 that he's got selected. Also, you can create a grip builder. So you got the animation step timer at the top there. You can put the step, move the sliders across, and it'll move the hands, and then you can add it to the grip, and you can create your own grip sequence. And we did this using the app to create Caden and Xbox grip. And then going back into the menu, this flyout menu is all part of Xamarin Forms shell. I highly recommend you go to docs.microsoft.com and look up on Xamarin Forms. And look at the shell architecture. It's brilliant. Super simple. We've got the UART control, which talked about earlier, which is for me as the developer to send commands, but also a technician in the hospital to send commands, changing things like the muscles controls and the muscle sensing as well. But this is low level stuff. So we created a setting screen to change the hold times and the threshold peak times, etc. Enable and disable the motors. Set the muscle sensors, muscle modes, etc. as well. So that can all be done as well. We keep a lot of the stuff out of there so Caden can't break his hand because in his version of the app, the UART control is disabled. And then we've got the muscle sensor check. So every couple of days, Caden's prompted to go in there and connect his hands. And then he does open and close for just the muscles, and it'll move those 2 green bars up and down. And he does that. Change grip, does that, change grip, does that, change grip, as it says, and it records a sensor values. It's sent up to an Azure function in the cloud, stored in in the cloud in storage. And the idea is that we'll then come back later and get a machine learning model to learn how to adapt those sensor values in the settings as well. So I'm just going to disable that. The reason you hear the whining is because I have the motors tuned so that I can hear them, so I know when they're on. And also when it's tuned out of our audible range, it drives my dogs bonkers because it's still in their audible range. We will get that done. I do the builds in Visual Studio for the Xamarin project. I then do a git push, goes up to GitHub and is stored there. App Center, a free service from Microsoft as well, is monitoring that build pipeline, that GitHub push, and pulls it in and does a dev build for me and pushes it down to my phone. And if I push to main now, this slide's old actually. If I push to main, it will do a dev build and push it to Caden and his parents' phone and the other people who are involved in the project as well. It'll push to their devices because I've made a major change. I want to push to them as well. App Center pricing is free. There is a paid for tier as well if you want more build minutes, but 240 build minutes is, a lot of build minutes for building mobile apps. It's pretty darn quick. So drawbacks then. We said earlier we've got rid of the malware sensor because we've gone to the sensor from SparkFun, and I bought them from Amazon now because they sell them as well. We got rid of the processor by going to an Adafruit board, and we got rid of the grips now because now we can do it all with the Xamarin Forms app. And Caden's got his Xbox grip, which is awesome. He can now play his Xbox with his friends, and he's got it set such that the grip is that when he opens and closes, it does a trigger finger. So he can shoot as quick as his friends can, and it holds that so he can then use his other two, his thumb and his finger, which is on his other hand, for moving the joystick and pushing the buttons. And to see him use this is phenomenal. It's really, really clever how he's adapted to using this. But he can now play his Xbox with his friends. So this here is a total project. You can see the two sensors. The Xamarin app is open source, so on my GitHub you can go out there and see. There's a private GitHub at the moment for some work we're doing, which hopefully I'll release soon to the public preview. So there is some bits there that are not the same as the app you've just seen, but you can go up there and download it. All the STL files, 3D printing, all the circuit designs are up there on GitHub. Download it, build one for someone, or even for your desk because you want to show off that you've got one. But all the components, the whole lot comes to just over £500 or $680 for all the components to make one of these hands. I've got some motors on my bench behind me, which I'm trialing in the hands in this one here to see if I can switch out these motors because they're the most expensive part. They're best part of £85 to buy in. They're shipped in from the US. If I can get rid of those, I can reduce the cost drastically and get it down to £200-300, which would be awesome. So what's next? Build out the Xamarin app as we're doing. Connect it to machine learning to send the values back to to change the settings within the app, which then gets sent back to the hands. Go full .NET, and we're going to use the Meadow board for that because that's .NET onboard IoT. If you've not heard of that, go out to Wilderness Labs and look up their Meadow board, the F7. Awesome. And I'll skip over that. Why do I mention being a pilot at the very beginning? It's because the plan was this 3D printer that my 11-year-old son built without any help. I was going to put in a box with some filament and some of the parts that are needed and take it to a part of the world and meet up with a hospital unit. There's a hospital in Pakistan that are interested in hosting me, and they're going to take this 3D printer. I'm giving it to them free of charge. I'm going to teach them, fly back to Forge every now and again to help them build prosthetic limbs for the children there. So giving back to the community, and that is the aim. If you know of another hospital unit somewhere else in the world, maybe in your local area that wants to learn how to do this, please reach out to me. My Twitter is there. I'm on Twitter, and let me know, and we'll see if we can hook up and sort of thing out. Everything that's in the box comes to less than £1,000, and they can make about 15 hands with that. And then they need to start buying their own filament and springs and nuts and bolts and things, which is, as we said earlier, is very, very cheap. So that's why I mentioned being a pilot. That's my talk. I want to say thanks to Caden and family. They've been awesome in helping this journey over the last couple of years.